the previous session I wrote some concepts like three-phase converter, Thyristor-based converter. So in that concept, I discussed about the rectifier operation and operation. And after that, I discussed about valve voltage, computation failures, and next AC current harmonics. And now in this class, I'm going to discuss DC voltage harmonics and current step converter and comparison between voltage source converter and current source converter. Okay, let's get into the point. So firstly, I will discuss the DC voltage harmonics based on a thyristor-based converter. So actually, it is purely based on the DC voltage harmonic. That is the DC side. So on the DC side of a converter, the output voltage is of a which depends on the pulse order, angle of delay that is alpha, and angle of commutation that is gamma. Okay. So here the output voltage consists of a DC voltage on which are superimposed a number of harmonics. Okay. So in this one, the output voltage consists of a DC voltage. So that is the output we have. Okay, on which are superimposed a number of harmonics. So that means it consists of a number of harmonics. So these have an order of n. These have an order of n. So it is equal to Kp. So here where k is an integer and p is the number of the pulses we are using. That is here is 6% means we have p is equal to 6. Okay, next with zero delay angle. With zero delay angle, that means alpha is 0 and no load or neglecting commutation angle, that is gamma. The RMS amplitude of each harmonic is given by, that is Vn is equal to V0 into root of 2 by n square minus 1. Okay. Next. So here the sixth harmonic has an amplitude of 4.04%. So here we have the harmonic. So in that one, particularly I am taking the sixth harmonic. So for example, I am taking thus the sixth harmonic has an amplitude of 4.04% and 12th harmonic has amplitude of 0.99% of the fundamental DC voltage, that is V1, etc. for zero delay and commutation angle. So this is for only the delay angle is 0, that means alpha is 0 and commutation angle gamma is 0. So at that condition, the harmonics has this much of amplitude, like the sixth harmonic has an amplitude of 4.04% and 12th harmonic has an amplitude of 0.99%, like that too for the fundamental DC voltage only. Okay, so with reference to the figure, so diagram 4.13, that is the in the previous concept. So the diagram I am taken into reference to this concept. So for harmonic analysis, so in the AC current harmonics also we taken some diagrams. So in those diagrams I am taken one diagram. So it is taken as a reference. So with reference to the diagram, the harmonic analysis with an angle of delay, that is alpha, and commutation angle delta gamma, the 60-degree segment of the DC voltage waveform can be defined in three parts. So reference from that diagram, we have three parts: the DC voltage, that too for the 60 degrees. Okay, so these are the three parts we have. First one is ES is equal to root 2 capital E cos of omega t plus pi by 6 for 0 less than omega t less than alpha. And one more thing we have, EL is equal to 1 by 2 root of 2 E cos of omega t minus pi by 6 plus root 2 E cos of omega t plus pi by 6 for alpha is less than omega t is less than alpha plus gamma. Here the omega t lies in between the alpha and alpha plus gamma, and u is equal to root 2 E cos of omega t minus dou by 6. This is for the omega t is lies between alpha plus gamma and pi by 3. Okay, so like that we have the three parts, the DC voltage waveform for the harmonic analysis of the DC voltage. Okay, so with refer to the diagram, this one, refer to this diagram. So this is the DC current and voltage waveform definition for harmonic analysis. So taking this diagram as a reference to present concept, the DC voltage harmonic, the DC voltage waveform consists of the three parts. So I already discussed those three. Okay, so this is the reference diagram. So in that one we have alpha and alpha plus gamma and alpha plus 2 pi by 3 and alpha plus gamma plus 2 pi by 3, like that we have. And next we have the parts, that is voltages ES, ET and EU. These are the three parts we discussed in the previous slide. So for the DC voltage for the 60-degree segment. Okay, so next we have the currents, that is IP, IQ and ID. Okay, so these are the current phasors. Okay, next. So here I will show three more diagrams. Those three diagrams shows the characteristics of harmonics as per unit of ideal DC voltage, that is V0 against the commutation angle gamma. So I will show the three diagrams. Those three diagrams consist of the characteristics of harmonics by taking the parameters like per unit of ideal DC voltage, that is V0 against the commutation angle gamma. So at that time we are using different values of delay angle alpha for 6th, 12th and 18th harmonics respectively. So it is seen from these characteristics that we have for small values of angle gamma, the harmonic magnitudes increase with the increase in angle alpha, and the higher the harmonics, the more rapid the increase. So if the higher the harmonics means there is a increment in the angle also. So for a constant angle alpha, the harmonics decreases. Why? Because they may increase slightly at first for small angles of alpha. Okay, so firstly it will increase, slightly increase, not more, but slightly increases and reach a first minimum at approximately gamma is equal to pi by n. So for gamma is equal to pi by n plus 1 and gamma is equal to pi by n minus 1, the harmonics are constants for any angle alpha. So at gamma is equal to 2 pi by n, there is a maximum, and at gamma is equal to 3 pi by n, there is a further minimum. Okay. Next, so when two 6-pulse converters, one with star to star transformer and the other with star delta transformer are connected in series to form a 12-pulse converter. So if you want to form the 12-pulse converter, we have to use the two 6-pulse converters. Okay, so one with star to star transformer and another with star delta transformer. So here the harmonics that are of the orders that are odd multiples of 6, that is 6th, 18th, 30th, like that we have, and will be equal and opposite in phase and cancel out, whereas the harmonics of the orders that are even multiples of 6, that is 12th, 24th, 36th, will be in phase, even multiples. So odd multiples means 6 into 1, that is 6, 6 into 3, that is 18, 6 into 5, that is 30, 6 into 7, that is 42, 6 into 9, that is 54, and 6 into 12, that is 66, like that the harmonics order will be appear. That will be equal and opposite in phase and cancel out. Same, whereas harmonics of the orders that are even multiples of 6, that means 6 into 2, that is 12, 6 into 4, that is 24, 6 into 6, that is 36, 6 into 8, that is 48, 6 into 10, that is 60, like that we have. Those are will be in phase. The odd multiples of this harmonics is in the equal and opposite in phase and cancel out, but the even multiples of 6 will be in phase. Okay, so obviously the current harmonics on the DC side are a function of the DC side impedance for each harmonic voltage produced by the converter. Okay, next. So these are the diagrams I am going to discuss. So this is the first diagram. So here I am using the variation of 6th harmonic. So that's why I am taking here the order is n is equal to 6. Okay. So harmonic voltage in relation to the angle of delay, that is alpha, and commutation angle gamma. In relation to these two angles, I am using this 6th harmonic voltage in relation variation of this one. So here we have different curves is there. So these curves are represents the particular angle. So suppose if the angle is 0, we have one curve, and if the angle is 5, we have one more curve, and like that up to we have up to 60 degrees. Why? Because here we are using up to 60 degrees only. Okay, that's why I am taking up to 60 degrees. We have these types of curves. Okay, and next one more diagram is there. So this is for the variation of 12th harmonic voltage in relation to angle of delay, that is alpha, and commutation angle gamma. So here the order of the harmonic is 12, n is equal to 12. These are the curves for the particular harmonic, 12th harmonic. And one more diagram is also there. So that consists of the 18th harmonic. So variation of 18th harmonic voltage in relation to angle of delay, that is alpha, and commutation angle gamma. Okay. So here also the order of the harmonic is 18. Okay. So these are the sum diagrams. These are the sum diagrams. It will give some clarity about these variation of harmonic voltages. And coming to the next concept, that is current source converter with turn-off devices. Current source converter with turn-off devices. That means a current source converter with turn-off devices is also referred to as current step converter. Current step converter. So actually in the previous classes, that these turn-off devices must have reverse withstand voltage capability. So reverse withstand voltage capability that comes under the symmetric devices, or have diodes in series if they are asymmetric devices. Okay, turn-off devices must have the reverse withstand voltage capability, that is symmetric devices, or if they have the diodes in series if they are asymmetric devices. Okay, next. So in the current source converter with conventional thyristors discussed previously, the operation of converter is limited to the third and fourth quadrant, that is lagging power factor. So actually in the previous class I discussed about some operational zone of the AC current harmonic, that is the converter, operation zone of the converter. In that concept I discussed one circle is there, it consists of the four quadrants, but the operation limited to last two coordinates only, that is the below coordinates. It consists of the horizontal hatching, okay, and remaining upper two quadrants are empty. So the concept I am discussing here. So in the current source converter with conventional thyristors discussed previously, the operation of converter is limited to third and fourth quadrant, that is for lagging power factor. Next, this is because thyristors do not have turn-off capability, they only have the turn-on capability. Okay, and the DC current has commutated from one valve to another, while the anode cathode voltage of incoming valve is still positive. Okay. Next, so also such a converter needs an AC voltage source for commutation. So if that converter needs an AC voltage source for commutation, so in the voltage source converters, there is the DC capacitor which facilitates rapid transfer of current from an outgoing turn-off valve to the opposite valve in a phase lag. So irrespective of the direction of the AC current. Okay. The capacitor is assumed to be large enough to handle alternate changing and discharging without substantial change in the DC voltage. So with turn-off capability, the valves can be turned off at will. Okay. However, turn-off devices, in order to turn off, still require an alternate path for rapid transfer of current. Okay. So if the turn-off devices, in order to turn off, still require an alternate path for rapid transfer of current. Next, so otherwise they will have to dissipate a large amount of energy to turn off current in an inductive circuit. So if you take the inductive circuit, they will have to dissipate a large amount of energy to turn off the current in an inductive circuit. Okay, so it can visualize that if a DC AC capacitors are placed on the AC side of the valves, AC side of the valves, they can facilitate rapid transfer of current from outgoing turn-off valve to the incoming valve. So here I am putting the AC capacitors on the AC side of the valve, that is the thyristors. Okay, AC side of the valve is nothing but the thyristors we are using on the AC side. Okay, so here I will show the diagram. You will understand this one. So on the AC side, I am using the capacitors. So here, if you look at this, so on the left side we have the 6 thyristors. That means 6 valves we are using, and it consists of the DC current ID. And on the right side, that is for the AC side, we have the here we have the three phases A, B, and C. These three phases are connected to the transformer. One is with the star or delta, and another connection is with the star connection. So the AC set consists of the different capacitors. Okay, so it is a passive load we are using. Okay, so based on this one, this commutation of current from valve 1 to valve 3 is illustrated in next diagram, that is the waveform. So previously I shown the circuit diagram for this operation, and next I will show the waveforms of this commutation of current from valve 1 to valve 3. Okay, so here the low inductance of the AC shunt capacitor and the bus connections, the transfer, that means commutation is rapid, and there is no commutation angle to speak of as far as the valves are concerned. Okay, actually with due respect to the turn on di by dt limit of the devices. So here I am discussing about the current, means I am taking the di by dt. So if I am discussing the voltage, means I am taking the dv by dt. So with due respect to the turn on, that is di by dt limit of the devices, inductance of the capacitors and the bus connections can be duly exploited. Okay. Also, it is to be noted that when a valve is turned off, valve 1 in figure 4.23, so I will show the diagram. Next, so its rate of rise of voltage is caused by the AC capacitor, and details of turn on and turn off in a few tens of microseconds time frame of the commutation is not discussed here. So here I am not discussing about the turn on and turn off capability. Okay, I am discussing only if you use the turn on devices in place of the turn off devices, what will happen? I am discussing. Okay. Next, I will show the valves diagram waveform. So this is the circuit diagram we have to use for the commutation process. I am not using 6 valves. I am just using the 3 valves. That to 1, 2, and 3 valves only. So that to the current is flow in only 1 and 2 valves only. Okay, here the current is transferred from valve 2 to valve 1. So here I am using one inductor or a reactor. So this combination on the right side we have the capacitors. Okay, so these are all used for the commutation process. Okay, from valve 1 to valve 2 and valve 3. Okay, next, it is to be said that it is a complex and important matter in terms of device losses and snubber requirements. Okay, so these capacitors need to handle a sustained alternating charge or discharge current of the converter valves. Okay, actually we are using the capacitors on the right side of the diagram. So these capacitors need to handle a sustained alternating charge or discharge current of the converter valves. Okay, unlike the line commutator converter using conventional thyristors, this converter with valve leading power factor. Okay, and it existing AC voltage for commutation. No need to taking of the existing AC voltage for commutation. So it can in fact operates as an inverter into a passive or an active AC system. Okay. So next, so I will show the another diagram. So it shows the anode bus current connected to the anode valve. Okay, so I will show anode bus current connected 1, 3, and 5. Okay, and transfer of this incoming DC current from 1 to 3 and 5 to 1, etc. in a closed 3 valve sequence in a 3-phase converter. Similarly shown are the cathode bus current, that is even numbers, that is 2, 4, 6. Okay, so odd numbers, that is 1, 3, 5. And next we are using cathode bus current, that is the outgoing DC current and how it transfers from valve 2 to 4 and 6 and to 2, etc. in a closed 3 valve sequence. Okay, so the two sequences are phase shifted by 60 degrees and they together form a 3-phase full-wave bridge converter. Okay, the two sequences are phase shifted by 60 degrees. I already discussed this one. and they together form a three-phase full wave bridge converter. Okay. Next, I will show the waveforms. So these are the waveforms for the cathode bus current and an anode bus current and phase currents also. So the cathode bus current consists of a DC current, okay, DC current waveforms. So here the valves we are using, that is 1 and 5 valves, and for the anode bus current we are using 2, 4, 6 valves. And coming to the phase currents, that is IA, IB and IC, these are the current waveforms. So here I am taking 1 and 4 and for the A phase, and 3 and 6 for the B phase, and 2 and 5 for the C phase. Okay, for the 3 phase currents I am using this one. So these valves for the A phase, for the current in the A phase we have to use the 1 and 4 devices, and for the B phase we have 6 devices, valves, and 2 and 5 for the C phase. Okay. Waveforms for the this concept, current source converter with turn off devices. Next, consequent injected AC current in 3 phases. So if we injected a AC current in the 3 phases is also shown in the diagram, in the previous diagram. So which is same as for the conventional thyristor converter by detecting commutation angle, that is shown on the B diagram. Okay, so here the currents are injected without the support of AC system voltages, and therefore the phase angle and the frequency of this injected AC current. To understand this operation of converter, it is appropriate to visualize it as an AC current generator connected to the AC, and which is front-ended with AC capacitors. I will show the diagram. If we see the diagram, we will understand betterly. So this is the diagram. So this is the diagram we are using. So this is given the system interface. Okay, so it consists of AC currents, transformers, capacitors, filters, and one AC system. This is simply called a system interface of the product system. Okay. Next, so in fact applications, the interface beyond the AC capacitor is likely to be a transformer, okay, which may be followed by AC system and filters to limit the harmonics from entering the AC system. Okay, so in the previous diagram we've seen those devices also. So capacitor, AC capacitor is also there, filter is also there, transformer is also there, AC system is also there, and some currents, AC currents is also there. Okay, the AC voltage at the converter terminal is the result of the interaction of converter generated AC current with the AC system impedance and system voltage. So naturally, the injected current has to be coordinated with the characteristics of the AC system in terms of its frequency and phase relationship. Why? Because to ensure that the consequent AC voltages are acceptable. Okay. Next, so in the context of shunt connected FACS controllers, this converter will simply inject an AC current into the system with the necessary AC voltage to force such an injection of current. Okay, so that is for only the shunt connected FACS controllers. If the application is shunt connected FACS controllers, we use this one. So next, this assumes, of course, that the DC current source is capable of driving such a current. Okay, in the context of series connected FACS controllers, if we use the series connected FACS controllers, the AC current, so here we are using the AC current in the line, okay, would flow through the valves to become a unidirectional DC current. Okay, next, depending on the DC side impedance and the source, DC voltage of either polarity would appear. So this DC voltage is reflected back as the converter AC voltage, which in turn will influence the line current. So if for some reason the connection to the AC system becomes open, so suppose that the AC system connections are open, so the converter is blocked. Okay, the current bypassed by the valves, and the DC side voltage can quickly reversed to manage the bypassed current. So this is a normal practice in the HVDC. Actually, these type of problems occurred in the HVDC. So since the current waveform of the single 6 pulse converter is identical to that of the diagram in the last concepts. The harmonic content is given by the equation we have. So the harmonics of the order here is 6k plus or minus 1, where k is an integer, you know already these points. So here the RMS value of any term in that equation is given by the next equation, and the RMS value of the fundamental is given by in that one. So this one, so we have E is equal to root 2 E cos of omega t plus pi by 6 for 0 less than omega t less than alpha. Here the omega t lies between 0 to alpha. And next U is equal to root 2 E cos of omega t minus pi by 6 for alpha less than omega t less than pi by 3. So here unit values of these harmonics given by the values on the y-axis of figures. Previously I shown 3 diagrams for the 6th, 12th and harmonics are 18th harmonic I discussed it. So same repeat for this one also. So here various PWM concepts, that is positive modulation concept discussed for the voltage source converters are applicable to the current source converters. So PWM converter concepts I voltage concept also. Those concepts but at that time I discussed a PWM concept for the voltage converters. This is applicable converters also. So an advantage of the PWM operation is that the commutation capacitor the commutation capacitor will decrease. Finally, we are coming to the last concept of the source converter. So concept of the second chapter, that is current source converter versus voltage source converters. There are some advantages of current source versus voltage source converter. This first one is diode based converters, the lowest cost converters. Actually, we are using these diode based converters also. So the diode based, if control of active power by the converter is not required, okay, if control of active power by converter is not required, at that time we have to use the diode based converters. Why? Because it is the lowest cost converters. And if the leading reactive power is not required, then a conventional thyristor based converter provides a low cost converter with active power control. Okay, if the leading reactive power is not required. So in the previous case, if there is no requirement of the active power, there is no requirement of the active power control. At that time we have to use a diode based converter. And if the leading power reactive power is not required, then a conventional thyristor based converter provides a low cost converter with active power, reactive power, okay, thyristor control reactor. So the current source converter does not as the voltage source converters. Okay, the current source converter does not have high shunt as the voltage source converters, because the voltage source converter consists of the high short circuit current. So for current reactor. Okay, next. So for the voltage source converters, the capacitor discharge current would rise very rapidly and can damage the valves. Okay, next coming to the fourth one, that is the 6 pulse current source converter does not generate third harmonic voltage, and transformer primaries for a 12 pulse converter do not have to be connected in series for harmonic cancellation. So it is also relatively simple to obtain a 24 pulse operation with phase shifting windings. Okay, and next, in a current step converter, the valves are not subject to high dV by dt due to the presence of AC capacitor. So I already discussed this one in the current step converter concept also. So AC capacitors required for the current step converters can be quite large and expensive. So although their size can be decreased by adoption of PWM topology, that is pulse width modulation topology. So in general, the problem of a satisfactory interface of current source converters with the AC system is more complex. Is more complex. So next, continuous losses in the DC reactor of current source converter are much higher than the losses in the DC capacitor. Okay, continuous losses in the DC reactor of current source converter are much higher than the losses in the DC capacitor. So these losses can represent a significant loss penalty. So with the presence of capacitors which are subjected to commutation charging and discharging, this converter will produce harmonic voltages at a frequency of resonance between the capacitors and the AC system inductance. So this will give the adverse effects of this can be avoided by sizing the capacitors such that the resonance frequency does not coincide with the characteristic harmonics. So these harmonics as well as the presence of DC reactor can result in lower voltages on the valves and transformers. That is, valves is nothing but the diodes or thyristors. Okay. So next, widespread adoption of the asymmetrical devices, that is IGBT and GTOs, are the devices of choice for lower on-state losses, has made voltage source converter choice when turn-off capability is necessary. So the device market is driven by high volume industrial applications. You know already this one. And as a result, symmetrical turn-off devices have high voltage ratings and required operating characteristics, in particular the switching characteristics, may not be readily available until the volume of the facts market increases. So before facts, there is no availability of such applications. So after introduction of the packs into the market, the volume of this pack market increases. However, as the devices evolve, particularly with the evolution of advanced GTOs that we discussed in the previous concept, it is important to continuously evaluate the converter topology of choice. Okay, thank you. Thank you for watching this video. Okay.